Hi, it's Kate, and this is the second video for week 4 of Math 23B. We've already discussed linear change of variables and general change of variables, so the question really is, when should I change my variables and how should I change my variables? And so I'm going to discuss two different parameterizations or phi choices, changes of variable, that come up a lot in practice with multiple integrals. The first one I'm going to talk about is cylindrical coordinates. Note that in lecture, we're going to do spherical coordinate examples and then cylindrical coordinate examples, but I changed the order in this particular executive summary because I'd already talked about polar coordinates, and really cylindrical coordinates are just an extension of polar coordinates just in R3. So let's take a look at how we move from Cartesian coordinates, x, y, and z, into cylindrical coordinates. Here is a point P as it's specified by its x component, its y component, and its z component. And in the original space, that's exactly as we would specify it, x, y, and z. But of course, another way of describing where it is in space is to use, rather than x and y, r and theta to describe its location in the plane. Then add on its z component in space. So how does that work? Well, the length of this blue line, its length from the origin when it's reflected in the plane, or you can think about the distance from the z-axis. Again, r is always positive here so that we don't have multiple combinations of r, theta, and z specifying the same point. Theta, again, is the angle measure that we take if we start with an initial side along the positive x-axis and then move in a counterclockwise direction, and our terminal side stops there. That is going to be theta right in there. And then we just add on our z component here. Usually it's pretty tacky to keep the name the same, using the same variable name in both the parameter space and the original space, but note that nothing has changed in how we define z, so that's okay. Again, this is what x is equal to right here. This is what y is equal to right here, and z just retains its original identity. If we take a look at the Jacobian of this change in variable, we find its determinant to be r, and so when we actually express the general change of variables approach for how to integrate this original function in the original space, a function in terms of x, y, and z, over bounds described by x, y, and z, first, we want to change the bounds so that they are in terms of r, theta, and z. We substitute in phi, our change of variable, into the original function. So everywhere we see an x, we see an r cosine theta. Everywhere we see a y, we have an r sine theta. Everywhere we see a z, we put a z. So now we have a function in terms of r, theta, and z. We multiply by the determinant of the Jacobian, and then we integrate with respect to r, theta, and z. Now you might be wondering, when am I going to use this? Well, there are a lot of times where a region of integration can be expressed as in either spherical or cylindrical coordinates. Generally, if the boundary includes a portion of a sphere, spherical is going to work better. We're going to get to spherical in a moment. If it includes a disk at some sort of constant z, cylindrical is going to work better. So anytime you have something that looks kind of like a prism with respect to z, that's where you want to use cylindrical. If you want to be especially prudent, you can use both to check your answer. But let's look at spherical now. Alright, so here's how spherical coordinates work. Rather than denote a point by x, y, and z, we're going to now denote a point using three parameters, r, theta, and phi. Now, r actually has a different meaning here than it does in terms of polar coordinates or cylindrical coordinates. Note that in polar and cylindrical coordinates, that's distance from the origin and distance from the z-axis in R2 and R3 respectively. Here, this is distance from the origin in R3. So r means something a little bit different. That blue dotted line would have been the r of polar or cylindrical coordinates. Of course, polar is only in the plane, cylindrical in R3. But this is the r of cylindrical coordinates. This is the r of spherical coordinates. So we use r again only greater than 0. We also use theta. Theta has the same meaning as before, if you reflect the point down into the plane and you create an angle that's entirely in the xy plane, theta is the counterclockwise movement through an angle with the positive x-axis. And then phi is once you have a reflection down in the plane, this is the angle above the xy axis that we pivot through to get up to wherever we are up here. So r, theta, and phi. We certainly see here that trigonometry is handily at work in determining what x, y, and z are equal to. And one of the things that may throw you a little bit if you've taken multivariable calculus before and you've seen spherical coordinates before is that in a lot of multivariable calculus texts, phi is considered an angle down from the vertical. So phi ranges over an entire sphere from 0 to pi. The way phi is defined in the Hubbard text and the way we are going to use phi, note that phi is an angle up from the horizontal. So phi will be moving from negative pi over 2, which is down by the south pole, all the way up through 0, up to pi over 2. Because of course, angle measure is moving in a counterclockwise direction as it increases. So here we have how to express x, y, and z in terms of r, theta, and phi. And the Jacobian, as you can probably guess, looks totally terrible, but when you actually take the determinant, not so bad. It is r squared cosine phi, again, because of the difference of how we define phi. If you've taken a class before, you probably saw r squared sine phi as the scaling factor. For us, it is going to be r squared cosine phi. And as long as you stick with one particular definition and the corresponding determinant that you get, everything will work out fine. It's worth memorizing just so this is nice and easy in your head and you don't have to rederive them from scratch, though you probably should be able to if someone asked you to do this, what the change of variables formula looks like in this particular case. Note that f is now composed with r, theta, and phi. Everywhere you see x, y, and z, you plug in these identities in terms of the new coordinate system. We have our volume stretching and scaling factor, r squared cosine phi. We integrate with respect to r, theta, and phi. And here our bounds will be described in terms of r, theta, and phi when before they were in terms of x, y, and z. This formula is really important in physics, applied math, and engineering because a lot of the time you want to integrate over a sphere, and of course integrating over a sphere of a particular radius now involves integrating with respect to 3 constant bounds. If you're integrating over the unit sphere, right, r is going from 0 to 1. Theta is going from 0 to 2 pi. And phi is going to go from negative pi over 2 to pi over 2. Yes, there are some redundancies in especially phi in particular, because if we hold r constant and we make phi equal to negative pi over 2, we can change theta however we want, and it's always going to map to the same exact point down there on the pole, or at least along that axis. But that's okay, because that's really only happening on a set of volume 0. So those are the 2 different coordinate systems that you should definitely know. And now I'm going to talk a little bit about how do you make up your own coordinate system? What do you need to do? Alright, so inventing your own change of variable, maybe a little tricky, but it's always good to remind yourself why we want to change variables in the first place. Maybe instead of integrating over a region that's super complicated, we want to integrate over a rectangle. We want to switch everything into constant bounds. Maybe we want to integrate a function that's particularly difficult, and instead if we switch our variables, we would be able to exploit the fact that integrating a function that's a sum of products of functions of individual variables is much easier. If in fact your change of variable is able to describe a region using constants and transform a function so that it's a product of univariate functions, we actually are able to not even use Fubini's theorem and just reduce the problem completely to single variable calculus, because it's just going to be the product of single variable integrals. And even if ideally, our region isn't described as a rectangle, a triangle would be totally fine as well. Just something that's not super complicated. So when you encounter an integral of a messy function, or maybe you encounter an integral that's being integrated over a messy region, or maybe nightmare situation, it's an integral of a messy function over a messy region, the idea is that you want to invent a parametrization that gives the integral in parameter space the features above. It takes that messy region and it turns it into a nice, constantly bounded region. And it takes that messy function and it simplifies that function into something that's much easier to integrate. Some general rules of thumb as you do this. When you're changing into a different coordinate system, do not use the names x, y, and z. It will be completely and totally confusing. If you're changing into an R2 new coordinate system, use S and T or U and V. With 3 parameters, use U, V, and W. Parameters are the names that we give to things like R, theta, phi, things like that. That's what we mean by parameters. But don't use the same names again. If the region of integration in the original space has a curve like a parabola or a hyperbola as part of its boundary, invent a parameter that is constant on that curve. So if, for example, part of the boundary is the parabola y equals x squared, use a parameter where y over x squared is equal to a constant. If the function to be integrated involves an expression like x plus 2y, consider a parameter like v equals x plus 2y. The basic idea is that we want to find some expression that takes x, y, and z and expresses each of those in terms of your new chosen parameters. Because that right here, this is what phi is. It's x written in terms of your parameters, y written in terms of your parameters, z written in terms of your parameters. Then take that Jacobian, get the determinant of the Jacobian, that's your volume stretching and scaling factor, but that's the really key part. You will have to do some tricky algebra there. If you follow the advice of the above up here, if you are able to use a parameter like u equals y over x squared and v equals x plus 2y or something like that, note that you've kind of solved your problem, only you need one additional step because now you have your parameter identities equal to things in terms of your original space variables. So you have u equals something, v equals something, and so you need to do a little bit of algebra to be able to suss out what x is equal to, what y is equal to, what z is equal to. These things, u equals, v equals, those are actually components of phi inverse, not phi itself. Once you have phi though, after a little struggle there, some algebraic difficulty, the rest is straightforward. You just want to compute the determinant of the Jacobian, take its absolute value, and then work entirely in parameter space. Don't be concerned. A full example of this will be done in lecture this week, so you can see it at work before you take your chance at it on the homework, possibly on a quiz, etc. And as always, if you have any questions, please let me or Paul know. Available by email or during office hours. And this is the final week of material to go on quiz number 1. Lots of practice to be had using spherical, cylindrical, polar, etc. and make your own variables. We'll get tons of opportunity to practice these in class.